Hi everyone. So this is a pretty interesting problem in symmetry. This is problem number 3 from the Kevin Zhou E1 handout, and it's about a solid cube with uniform charge density, and we want to find the ratio, not the actual value, but the ratio of the potential at a corner to that at a center. This is a very interesting problem because it's a pretty elementary problem, yet it uses symmetry very well. So if you're starting out with electromagnetism, this is a good start to how we use symmetry in problems in electromagnetism. Now, with this problem, what you basically have is you have this solid cube. It has charge density rho, and there's some potential at the corner of this cube. Just randomly labeled it U naught, capital U naught, and there's some potential at the very center. Casually named it capital V naught. What we want to find is this ratio U naught over V naught. Now, the thing with ratios, which is important, is it's not the same as finding the actual answer. You don't really need to find the values of U naught and then the value of V naught and then plug in U naught over V naught. What we can instead do is just find a relation between the two. So let's say we solve this problem, which I'll do in a second, and let's say arbitrarily we found some relation that the potential at the center is 4 times the potential U naught. What we've done is we've just rewritten V naught in terms of U naught, and then this gives you the answer instantly because U naught over V naught just becomes 1 over 4. And that's how we solve ratio problems. We don't look to actually find the value of each thing that we want the ratio of. We rather try and write them in terms of each other, and from that we can find the ratio directly. And that's what we're going to do here using some simple like symmetry arguments. Now, what I'm going to do is what I just said was that I want to find one of these V naught or U naught in terms of the other. Let's look at U naught. How about we write this V naught somehow or the other in terms of this value capital U naught? There's actually a pretty interesting way to do it. How we do it is we take this cube, it has 8 quadrants to it. It has this quadrant over here, this quadrant behind that, this quadrant behind that, and this quadrant behind that, and then 4 at the bottom. What I mean by a quadrant is a smaller cube. So let me draw like a 2D analog to this. Right. Oh my god, that's not a cube. Okay. Very bad cube. But let me draw it in a 2D sense. We can divide this 2D square into 4 sides, right? 4 quadrants. And then when we draw a cube behind that, they'll all obviously we can divide it into 4 more behind that. So it would be kind of like this. This is a horrible drawing, but I think you get the point. This is 1 quadrant, we get this quadrant, we get this, and then this and whatever is behind that. So we can divide the cube into 8 elements. Now the basic advantage of this is we can use a pretty simple symmetry argument because look, when we divided the cube into 4 quadrants, let's name these 1, 2, 3, 4, 5, 6, 7, 8. Let's say this is cube 1. Now, the this corner of the cube, the far right bottom corner, actually touches the center of our big cube. If you just think about taking this smaller cube out of the bigger cube, this corner was touching this part of the cube, and this corner will have some potential at the corner, small u, right? uh, Take this one. Let's say this is cube number 2. This corner touches the big cube, and let's say that whatever potential is here will be the same potential here, because with a cube the potential at each corner of the cube is going to be the exact same at any other corner by symmetry, because why would it be different? You could literally rotate this cube 180 degrees, you would have this corner coming here, and the potential you would see as the exact same. So the potential at each corner must be the same. Now what we do is we keep doing this. So let's say this is cube number 3. This corner of the cube has potential small u. Let's say this is cube number 4. This corner has small u. This is cube 5. This corner has u. Um, and we keep going and labeling it, and yeah, so this corner 7 would be this corner, it would be this corner, and each of these has potential small u. Now when you take all these cubes and you combine them all together again and make a bigger cube, which is the blue cube, what happens is each of these corners, all of them are now overlapping and touching each other and existing at the same spot. So the potential here is just going to be, the potential at the center of the large cube is V naught, but this potential is just going to equal 8 times U, because we have 8 cubes with potential U, and when we join them together, all their corners combine to make the center with potential 8 times the potential of just one small cube. Now the problem here is this is not U naught, this is not this value big U, it's a small u. So how is this of any utility to us? Well, we can make another argument and actually find a value for u, small u, in terms of u naught. Now what I want you to think about here is, forget all this for now and just think about what we do when we find the potential. The formula when we look for a potential of a charge distribution is just the constant k times the charge over r, right? Now we over here we don't have charge, what we have is rho. So let's write that in terms of rho. We would have k rho, and now this would multiply by some volume. This is not an exact value for a cube, we're just finding the sort of the dimensions for it. The rho would multiply by some value in r cube, because volume is of meter cube. So let's just say this is some value r cube. Okay, now this is divided by r, so what we get is k times rho times r squared, where r is the dimension of our system, is the dimensions of this cube. So what we've basically found is that the potential at a corner of this cube or at any place in this cube is going to be proportional to the square of the dimensions here. Now the reason this is important here is because when we divided this cube into 8 pieces, what happens is each of these pieces, let's say this side length is a, this side of the cube is a, each of these pieces is going to have side length a over 2. All of them are going to be a over 2 because that's the way we divided our cube. But the potential is proportional to r squared. So when we half the side length, the potential quarters. So what I'm saying is u naught must, small u must equal u naught over 4, because when we half the side length and the half the dimensions, we have to quarter the actual potential of the cube here. So then we just directly get our answer, and that just becomes 8 times u naught over 4, which is 2 u naught. This isn't the answer we wanted. The answer we wanted is u naught over v naught. So that just becomes u naught is u naught, v naught we found to be equal to 2 u naught, and this just becomes half, and that's our answer. This is a pretty important question because it looks at how to use the ratio method. Like whenever a question asks for a ratio, it looks at how to tackle the question in terms of finding the the variables that we're finding the ratio of in terms of each other. And it also looks at a pretty nice and pretty neat and interesting symmetry argument, going from this big cube to 8 smaller cubes. So yeah, that's all I want to cover for this video, and thank you all for watching, and bye.